Hey! Oh, that's absolutely awesome. Hello and welcome back. Okay, in the last VGA video, I built an 8-bit DAC. Now that was kind of a test of the circuit. My final plan is to have 3 of those on one PCB module. But in the meantime, I've gone on and made 2 more of those test PCBs. And now I'd like to actually integrate them into the main build and see what kind of color reproduction we can get out of the system. Let's take a look. Okay, so I've got 3 of these DAC modules now. I still plan to make a single PCB with 3 of them on, but for now that's what we've got for testing. Let's have a quick reminder of what the VGA can do in its current tile map as frame buffer configuration. Okay, so I've loaded up a version of my standard test Parrot. Now, compared to the last time I showed this in color, I've turned off a feature in my converter called dithering, which tries to create slightly more color variation by introducing some semi-random patterning into the image. So I wanted to demonstrate the kind of raw color reproduction here. And what we're getting is quite limited because of the 3 bits of red, green and 2 bits of blue we've got here, because we're taking the 8 bits out of the back of the tile map and trying to interpret that as color data. And that was only ever a temporary thing. That wasn't the long-term plan. So what I'd like to add today is a hardware palette. So let's take a few minutes just to talk about what that actually is. Okay, before we talk about the palette, let's talk about the current implementation. Coming out the top of the tile map, which we're currently using as a frame buffer, we've got 8 bits of source data, and temporarily we've made 3 DACs for red, green and blue, and we've wired the low 3 bits of that output into the red DAC, the next 3 bits into the green DAC, and then the remaining 2 bits we used for blue. Now I have labelled these 8-bit DACs, but we only built resistor ladders with the correct number of bits in there to save breadboard space. But in the plan for the final circuit, and even on breadboard now I've built the 3 DAC modules, we've got 24 bits. So the palette is a way of converting the 8 bits of source data we've got into 24 bits of output. And to do that, we use a palette, which is also known as a color lookup table. With 256 entries in it, we use the 8-bit input to look up into that table, and then we can directly output 24 bits from that table into the output DACs. Now the clever people will have spotted that this is actually only 768 bytes of data. So we've got 256 entries in the table, and each entry requires 3 bytes, 1 for each of red, green and blue. But when we organize this in memory, I'm going to stick an extra byte of padding in between. So then each of these palette entries are 4 byte aligned, and that's going to make life an awful lot easier both for the circuit and for the code that's programming it. So now we need to talk about how we're going to implement it. Now we need the lookup for the red, green and blue components that all happen simultaneously. So I think the most straightforward way in circuitry to do that is to have a separate RAM chip for each. Then when we're outputting color data, we're going to use the 8-bit index to drive the address lines for each of those. The active low output enable, we're just going to pull that down to ground, and the active low write enable, we're going to pull that high. That's a pretty straightforward circuit for reading data back out, but we do need to think about how we're going to write data into these RAM chips. When we built the memory interface board for the VGA, we created output selection lines for each of the allocated chunks of memory, including the 1 kilobyte for the palette. And that region select line will go low for any write to the 1 kilobyte region we've put aside for the palette. Now that means we've got 10 active address lines that we have to worry about here, and I'm going to take the upper 8 of those and drive the address of all of those RAM chips simultaneously, and we'll do that with exactly the same multiplexer logic as we interface the RAM in the frame buffer. And then to index the individual components in each of those palette entries, we're going to use the bottom 2 bits of the address bus to drive a demultiplexer, which will distribute the write enable line to the individual RAM chips that are relevant at that point in time. Now we also need to put the written data onto those color output lines. So we're going to introduce line drivers that can push the data from the memdata bus into the inputs of those RAM chips. We need the output enable for the RAM chips to be the opposite that it is for the line driver. That's going to be coming from the region select line, but we'll use the same trick we used on the frame buffer using one of the multiplexers to make sure that signal change happens simultaneously. And if you pay attention, you'll realize that what we've got here is almost exactly the circuit that we built for the frame buffer, only we replicated the actual memory section 3 times and added this demultiplexer. And the address lookup comes purely from the color input, and we don't need to mess around with the counters that we used for the horizontal and vertical position. Before we go on and build it though, I would like to just mention that there is an alternative. The original IBM VGA cards and many other similar graphics adapters used a RAMDAC chip, and you can still get those. Now these do essentially the job of the circuit we're building combined with the output DACs. You've got 768 bytes of internal memory, you've got the index driver input, and then the output is the 3 analog signals. So the entire combined circuit between the palette board and the output DACs could be replaced with this one chip, plus a little bit of driver logic to map it into memory. I don't want to use one of these, I want to build it from scratch, which is the underlying principle of this project build at the moment. But if I go on and do some future VGA work, I may well use a chip like this just to simplify the circuit and not retread the same ground as we're currently doing. So let's take a look at building this circuit. Right, okay, so I've actually got a facility in this Parrot display code to show me the 256 colors we're currently dealing with. And you can see here the various patterns I've got that show the 8 levels of red, 8 levels of green, and 4 levels of blue. That's been working okay for us, but if we had custom picked colors, we would be able to display these parrots an awful lot better. And it introduces a whole lot of extra functionality to us if we've got that functionality as well. I would like to look at the wiring we've got here that's going to help us introduce that hardware though. So I'm going to fire up the oscilloscope and we'll look at some of those data lines we created when we made the memory interface board. Right, firstly, we've got the memory region line for the palette. Now that line should go low whenever we're doing a memory write into the 1 kilobyte we've put aside for storing the palette. And we've also got the memory load line, which should be offset half cycle of that, which is the signal we want to feed into the write enable line on the RAM chips. Okay, let's try and initialize a memory write to that palette region. Let's give that a try. Okay, that's roughly what I was expecting, although the write pulse is slightly earlier than I thought it would be. I might need to investigate that a little bit more in the future. But let's double check it's actually behaving in the way we expect. So this byte should be the first byte in the frame buffer, but it shouldn't affect the palette output. Okay, so we see that top left pixel's changed, but we didn't see the scope trace change, so that seems to be selecting what we're doing correctly. Now we've got the 8 data lines, and only the bottom 10 bits of this address data should be relevant to us for that 1 kilobyte region. But I think we've got everything we need here to actually go off and start building the palette hardware on breadboard. Let's have a go at that. Okay, I think I can fit this circuit into 4 breadboards. I've got 3 of these DACs, 3 of these 7164 RAM chips, and 3 of these 541 line drivers. Now I had hoped to use one of the very small RAM chips, but it looks like they're not really in production. So what I'm going to do is use these 8 kilobyte RAM chips that I used for the frame buffer, just because I've got a number of them lying around and they're a produced part. I've got a few ideas on what I could use the extra space for, but I'm going to ignore that today and maybe experiment with that in future. Bridge the power rails together. Now, I want to tell you about something that's been frustrating me. Now, normally when I'm designing a circuit like this, I've got a rough idea on how it's going to go together, and especially it's usually straightforward to come up with the rough set of parts I need. So I've been trying to work out how to assemble this. Now, I do like to cut the majority of wires before recording a video. So I've sat down and I've tried to plan this out. My first thought was to put the DAC there, have the line driver there, and the memory chip there. Now the inputs to the DAC are on this side, so I would actually have to put the line driver upside down to make it easy. So I could cross connect here, then take the data outputs from there to the top. I would need to extend the data inputs to the line drivers down for 3 of them to replicate the circuit out for red, green and blue. And I do a similar replication for the address lines, which were going to be the index or address inputs. And then I'd have the multiplexing logic and the demultiplexers down here to handle the rest of it. The problem is when I started cutting the wires for that, I realized the job was going to be really difficult. Then I came up with a new plan. I'll put the DACs across a circuit board like that. Put the memory chips across on this breadboard. And then the line drivers are crosswise like this. And that would mean that those big bundles of 8 data lines would be kind of transitioning up the board. I still have to get the data lines and the address lines to go horizontally across, but I think this might be a better way of doing it. So I've got these output lines to line up exactly. Now data lines, we've got 5 there, which I want to line up with those ones. Ground line's going to be at an angle there, but I think I'll have to live with that. I've got 3 data lines from here I need to bring up. Okay, that's actually still tight. These grounds at the top are slightly longer. Okay, so that's power and ground for all of those chips. Now we've got 2 output enables on these line drivers, so I'm going to bring one of them down. Now on each of these RAM chips there's address inputs we're not going to be using for the time being, so I'm going to bring those low. A12. It's 8, 9, 11 and 10. Alright, now the chip select 2 line. I'm going to pull that high because it's always doing something. Now chip select 1 is active low. We need to pull that one down. So now on each of these we've got the right enable line. Those are going to come from unique locations on a demultiplexer. The output enables, we're going to tie those together, and then the outputs need to come up to both the outputs from the line driver and the inputs to the DAC. Okay, so that's the simple wires. Now I need these data lines to come up to here, as there's 3 underneath. The address and data lines I need to appropriately cross connect. Bring the data outputs to the outputs from the line driver and the outputs from the line driver to the inputs to the DACs. Cross connect these, which are going to be the mem data bus. Cross connect the address lines, which are going to be either the color index or the 8 bits of address at the top of our 10-bit region. Okay, I've got lots more wire cutting to do. Okay, so I've been cutting some more wires. Firstly, I want to connect the line driver outputs to the DAC inputs. Now it's going to be slightly easier, I think, if I use the lower enable lines. So I'm going to take these ones out and pull the upper ones low. It's also reducing the contention down here for the ground rail. Okay, so the inputs to these line drivers are going to be the mem data bus. So I need to cross connect all 3 of those. And I do need to connect it up to one of these lines. And I'm not going to be able to kind of add this in here to pick it up because I want wires to come down and match all 3. So I think what I'm going to do is take a set of wires out to create 8 lines here, and then daisy chain onto those. Now, is there a good way to test that before I move on? Okay, actually gives me a lot of confidence those connections are good. It's always worth double checking when you've got lots of chained on connections like this. Now I want to take the outputs here down to the data lines of the memory chips. That aligns with the fourth one along, so I've got all of these chips off by one slot if I want to keep my lines parallel. That's annoying. I also noticed pin 1 here is not connected and pin 2 is address line 12. Good thing I spotted that while I was wiring. Alright, so those first 5 data lines are easy. These are the top 5 numbered bits on the diagram, but we don't actually care about the ordering at all. If we swap 2 bits around when writing the data in, and then it gets read out from the same locations, it doesn't matter, it will still be correct. Now, the 3 lower data lines are over here, and they're a little bit more complex to pull out. Now, I could just create longer, bendy versions of these wires, but I think what I'd rather do is come down to the same location, continuing on. Now I need to take the 3 lines from here across to here on each of the 3 channels. Now the first time I did something like this, it was ROM chips with sockets, and I actually took the wires out in the gap underneath the socket. Last time I used these low profile RAM chips, I cut custom wires that shaped around there. But this time I'm going to do something slightly different. First I'm going to bridge between the 2 sides of the breadboard here. And then I'm going to bridge horizontally to create the connection I need. Very simple reason for doing this is it's a big increase in the likelihood that I'm going to be able to reuse these wires in the future. I don't want to know how many wires I've cut and since discarded over the course of this project. That's good. These are the write enable lines. They need to be driven separately. That's the output enable line. I'm going to tie those together. Now the copy and the blanking lines need to be tied together as well. Excellent. And now those 8 address inputs need to be cross-connected. I think this technique of using slightly raised cross-connections where I need to put lots in the same space, this works out better than this technique. Alright, that's good. Once again, these are very important, so I'm going to try and test them before I go further. That's promising. These lines here are a manifestation of mem data. It's easy enough to pick up and connect back to the system. But the lines that are coming in here to the pink lines, those need to be multiplexed between the color index and 8 bits out of the address bus. So we actually need to start building some logical circuitry. And that's going to work exactly the same way as it did for the tile map frame buffer circuit. I'm going to use these 157 multiplexer chips. Right, so I've got 8 lines coming in for the address and 8 lines coming in for the data. If I put the multiplexers either side like this, I think it was going to produce the shortest possible lines. These are a bit unwieldy at the moment. Just going to put that in as a proxy. Just notice the power lines lined up with a gap there. Put those in to demark where the ribbon cables are coming from. These are going to need power and ground in the usual spaces. And there's an active low enable pin 15. And then we've got 8 sets of input-output lines to deal with. Right, so that's input 1 from the top. So input 2 on the same channel from the lower set. Right, so that's 1 of 8 channels done. Right, so that's 2 done fairly neatly. I think I'll probably do the next pair on the top sides. Now, I'm almost certainly showing the design of this circuit via the EDA package, probably over there somewhere. And the chances are the pin ordering I do on there is not going to match what I do here, but it doesn't matter, as these are 4 common circuits which all do the same thing, and I'll be wiring them differently on the breadboard in the EDA software, and I'll possibly reorder them again when I convert it to PCB, just to make the wiring as neat and as in order as possible in all 3 locations. Okay, halfway. That one's wrong. I've put that into a 1 space. It belongs in a 2. Okay, so that's all 8 data inputs done. I still need to bring the outputs for the bottom 4 up, but while I'm here I want to tie together the AB select lines. I think my only choice here is to go over the top of these chips, which is why I left these ones to last. Okay, so that's all the inputs and outputs done, so we should try and test those before we move on. Actually, this one kind of gets in the way there. I should fix that. I'm just going to kind of mark where these go. So that's 1 set of inputs. That's the AVA. Right, so I've got a little bit more work for me this time. I'm going to feed that into the register input. Move these test LEDs down. It's going to be easier to put this the other way around. I do basically just want to test as much as I can as I'm going. So it's the selection. So at the moment we've got all 0s and all 1s, and we're getting the all 1s out. So we pull select high. Now that's, since this is going to come from the memory region line, that means we should be getting this low side, which is the color index. Those are all coming out okay. And if we switch these over and switch that low, we're now getting the address lines. And they all seem to work. So now we need just the memory interfacing logic, and we need the demultiplexer to select which one of the memory chips is being written to. Okay, so we need to add support for these enable inputs. Now we used a 157 in the tile map board, but I've been thinking about that, and there's multiple ways we could do that. Because on that board, we use 2 channels for the control signals and 2 channels for address lines. And because we're actually keying that off the same selector, then that works for us. But on this board, we don't need those additional lines. So I'm kind of perturbed that I'm kind of wasting half of this chip. Now, I could do exactly the same job using a 138 demultiplexer. I could even do the same with 1/2 of a 139, but the other half of the 139 isn't enough to do the channel selection logic because we need 2 selection lines on that. So it's going to be 2 chips either way. I would like to think about that and find a way of dropping 1 chip out the system, because it feels like that's kind of avoidable or very close to it. But as it is, let's kind of reproduce the circuit we did in the frame buffer and tile map, just because that's going to make life an awful lot simpler for us to look at the circuits if we're doing the same thing. I do need to broadcast an enable line to the output enable on these memory chips and to one of the enable lines on these line drivers. And I think I'm going to have to go back on what I said before. I think actually direct wiring this lower one and using the one at the top, because then we've got the space for cross connecting. It's not uncommon to change your mind about the wiring routes as you're building a circuit on a breadboard. Okay, we need to pull that enable line low, the same as on the others. Right, this first channel, we're going to pull up on the first input and down on the second, and use that to drive the output enable on these memory chips. Now, by connecting the inputs like this, what we've essentially done is constructed an inverter. But the benefit is the inverted signals will keep pace exactly with any other signals we generate through these 157s, whereas an inverter on its own would actually be a lot quicker. There's a risk it would overtake and would have some contention between the output enable on the memory chip and the output enable on the line drivers. So these we're going to do the opposite way around. Now we need to worry about the right enable line. Actually, I can make use of another channel on here to help with that. Okay, so we bring the right enable in line there. So this should only pass through when the memory region select for the palette is enabled in a low state. Otherwise we want it to be high. This next one we're not going to use at all, so I'm just going to set its inputs as low. I don't always worry about that on a breadboard circuit, but I'd always do it on the PCB version. That's not strictly needed on a breadboard because these versions have pretty good pull-ups, but on a PCB version it's always smart to do it. Now finally, we need to separate the selection for the red, green and blue channels. So as mentioned, I'm going to use a demultiplexer, the 138. We're only using 3 of the output lines on this when it has 8, so that kind of feels underutilized, but I do have lots of these, so it's a convenient chip to use. I'm going to move that one further down so the ground line can be straight. First 2 lines here are the address input. The third one is essentially an unused address input, and we want to pull that down, and that's going to be at an angle. Since one of them has to be at an angle, I'd rather just have the even chip spacing. So we have an active high enable there, and we have an active low enable. I'm going to take that from the aforementioned output. We have another active low enable. I'm going to feed that off the same select line that all the other chips are using. That's not strictly necessary because this should only go low while this is low, but I kind of like the idea with passing the same enable line into everything. It's the address lines, bottom 2 bits. So then we've got 3 right enable lines that we can take off to the 3 chips. Now this configuration does mean that we have every fourth byte is unused. So we could put a fourth channel on here really easily. We could also maybe do a set of registers using that spare byte. I did think about doing that for the scroll registers, but if we kind of interlaced them with the palette like that, it would have been a lot less logical when you're programming it, and it would have meant I was needlessly moving the memory pointers around whilst doing all the beam racing demos I've already done. Right, so memory region line, memory write line, that's the bottom 2 bits of the address. And then we've got the upper 8 bits of address and the color index here. So pull that high will be the default. Same for the memory region. Now I'd like to test this as best as we can before getting the main build out, but that's actually getting pretty difficult now with all the controls we've got. I'm thinking if I wire some LEDs in there, we should at least be able to see some of the outputs working. I'm going to pull those address lines down. So I'm putting the bus output from the bus tester into the index inputs. Now if these RAM chips are anything like the ones we've used before, they should initialize with fairly random contents. So we should be able to at least tap through the addresses and see there's some garbage in there. Okay, well this looks like garbage and it should change when we change the color index. Okay, it's kind of what we'd expect. Now, if the memory region select goes low, that means what we're outputting on the data should be all the way over here. Now I've loaded this value onto the data register. So if I trigger the load line now, we should be loading it into channel 0, which is red. We put the select back to high. Well, that worked. I'm just going to fast forward this bit of testing as I'm just replicating different permutations of that write. It's already a long video, and with this number of control lines, it takes a while to reassure myself there are no glaring flaws. So region select, it broadcasts it everywhere, trigger the load line, release, and now we've got the red, green and blue bits in index 0 loaded correctly. Now because we've got more lines than we've got on the bus control, it's pretty difficult to test for different indices, but the readout for the different indices seem to be working correctly, so I think at this point we should prepare to plug this back into the main build and give it a proper test. Let's get the main build out. Right, so I've got the build out. Let's see if we can fit this in. Now we should be able to replace all the functionality of this breadboard. So we'll steal power straight away. Don't need that bodge anymore. This is the clock line that we use for copy. This head has got the blank horizontal and vertical sync on it. Let's get that over here. Blanking can go to the blank input. That should get broadcast to all 3 DACs. Right, so these sync lines, I'm going to try and just do direct links. We need these resistors to balance them. We're actually updating circuitry now we built in the very first video. And to the left of those is ground. And we stuck extra grounds in at the 2 ends. Okay, so that's the red, green and blue lines, and the red one reaches. In an ideal world, I'd actually break this cable out into the little coax bits with a 2-pin header on the end, to preserve the shielding all the way to the DAC. Okay, so we've got blanking, we've got the copy line. Now we need to worry about these main inputs. Our lower inputs here are the color index, which is what we were feeding directly to the DACs. I think I can recycle this as the memory data bus. This one was going to be a bit short. Then we've got the address bus. Now it actually plugs in 2 lines up, and then the lowest 2 lines of the address go over here. That's the memory write, and that's the palette region select. I think that's everything. Okay, I am going to recover some of these decoupling caps, spread them out through the build. And nothing left to do, but let's try and power it on. Okay, well, we've got some very randomized looking colors over here. That doesn't look like the same spread that we had on the previous directly wired DACs, so I guess that's promising. Now I've let the VGA circuit clear itself. Now that does imply that we're filling the screen with whatever the 0 entry is. Okay, so if I write 255 or FF in hex to the first byte in the palette region, that should be the red channel in index 0. That looks promising. Well, it's red. If I set blue to 255, I should get magenta. And if I set green, I should get white. Okay, now this is feeling pretty promising, so I'm going to see what I can do about some more interesting demos. Okay, so I've got a version of the Parrot's code here, which should hopefully have a fairly optimized palette. Okay, the first thing I'm going to say is that looks like the palette hardware is working correctly. The data's loaded correctly into the palette. We can see that the Parrots do look a lot better, but we do have this 1 pixel wide artifacting, which seems pretty stable. And my guess is these chips are not passing through the address quick enough. Okay, I kind of should have expected this. We were asking these chips to switch at full pixel rate, and they're not quite getting somewhere between the address being latched into here, the multiplexers taking it, passing it into the memory chip, and that outputting it to the DACs. We've got a race condition of 1 pixel. I may only be able to solve that with faster versions of these chips. Let's get the scope in and see how close it is. Right, so that's one of the index bits changing. Now let's look at one of the output bits. Yeah, that's not making, that's not very useful. It is curious the way that seems to improve slightly when I put the scope onto the copy line. Okay, that's interesting. All of the changes seems to be happening, or the majority of them seem to happen when the copy line is low. Is it possible I've just made a mistake on that? Right, so I just momentarily have inverted the copy line and we've actually made the problem lots worse. So that implies that our signals are correct, but the signal is just getting there slightly late, kind of what I feared. Okay, so the theory is that these are not quite switching fast enough because we can't do much about the speed of the RAM chips, but they should be fast enough, but we just need the index to get there quick enough. Now ideally we'd switch out to much faster versions. I believe these LS versions are very slightly quicker. Okay, that's slightly less issues I think. Maybe I'm kidding myself. Okay, that looks like we solved it. Okay, so yeah, I mean our Parrots look absolutely awesome there compared to how it was before. Now if it wasn't clear what the issue there is, the 157 multiplexer chips I was using were a slower version, and I'll be using the ACT fast ones that I used in the horizontal step for the tile map when I actually turn this into a proper PCB. And I'm going to order some ACT fast versions of these for the breadboard implementation in the meantime, just so we can confirm they're working correctly. And we've got some more boards to use where we need to switch those signals at the full 25 megahertz. Just the chips I was using, they're just not quite up to 25 megahertz switching, which we already know we're really pushing the line on the frequencies we can deal with on a breadboard at the moment. Let's not take any more chances with that. Okay, now I do have this mode here where I can show what the palette is. We can see there that the palette is far better attuned for producing the parrots. We've got lots of graduations of those greens, the reds and the yellows. So that explains why the parrots look so much better. And just for comparison, in this program, I've also loaded the original Parrot image with a palette that matches the old DAC layout. So there we can switch immediately between the old Parrots that we had at the start of this session and the new Parrots we've got now. So that is an absolutely awesome improvement. Prior to even building the circuit, I wrote this Parrots code because I added functionality for the palettes to my simulator, so I was able to write some sample code before I started building the breadboard, which is actually a really good way to do it if you have that option, because it means I've got a number of test programs that would have helped me diagnose what was going wrong, but also to give you a decent demo of the palette code. Let's take a look at some of those. Now, one thing to note is palettes like this enable us to make nicer looking images because the colors are better customized. But I'm going to be honest, that wasn't what I found exciting about this. Is actually the thing I really want to be doing to improve my games on this system is I want to be able to modify those palettes in runtime. So the rest of my demos are actually just examples of doing modifications for the palettes while the code is executing. First up is a bit of a classic. Now, a while back, I ported Matt Heffernan's Mandlebrot code, and one of the first times I ever saw palette cycling on a VGA device was actually animating the color indices of a Mandlebrot. So I've retrofitted some color cycling onto that code. Now, initially we have to wait for it to actually draw the Mandlebrot. This is full resolution, so it takes quite a bit longer than the low resolution benchmark test. Ha, that's awesome. So I've seen all of these demos run on the simulator, but this is the first time I'm seeing them run on the actual hardware. This is great. Okay, another interesting one is we've got 256 entries in our palette. So I did have a look at the idea of modifying palette entries between scan lines. Now we've got the same problem as the main tile map. If we change it whilst we're outputting data from the screen, we're going to create some corruption. But we can make some changes to the palette within the horizontal blanking interval and not create any issues on screen. Now, I've written some test code and I can pretty comfortably, I believe, change 3 palette entries in a horizontal blanking interval at the 4 megahertz I've currently got it clocked at. Now, with some very careful fine tuning, I can maybe make it 4, but I think 3 is a bit more comfortable. So this is a piece of test code I wrote which changes palette entries in each scan line just to get an idea of the maximum number of colors we can get out on the screen. And it works. Okay, so I've got 256 entry gradients for red, green and blue. I've got slightly less than that because we're only 480 pixels high for cyan, magenta and yellow. And we've got the remaining 253 entries in the color palette here. So this is demonstrating approaching 2,000 colors on screen, which I think is pretty good from a palette of 16 million. I'm incredibly pleased with this. This is working exactly as I'd hoped. So now we move on to the creative stuff. This is going to be interesting. What this is a static image, and people who've done any real-time graphics work will look at this and realize that the colors are what you would normally expect to see in something called a normal map. Now, normally the red, green and blue channels in an image are the appropriate intensity levels for red, green and blue light. But a normal map is a special kind of texture that we use in higher end computer graphics, where the red, green and blue channels represent the X, Y and Z components of the surface normal relative to the current surface. And the reason why I've uploaded this image is a technique I played around with many years ago is to use a normal map, but then use a lookup table, or in this case the palette hardware, to modify all of the entries that contain one particular normal. So I've quantized this down to 64 palette entries, and now I'm going to run a piece of code which will animate the palette but not change the underlying image at all. So what I'm doing is I'm changing each of the palette entries here to represent a light source that's moving against a white object moving around from the top on a left to right basis. I'm actually really pleased with how that's come out. Now I've got some thoughts to use this technique on a few more complicated objects, but that's going to come down to some experimentation. So you might see this in some hopefully cool looking demos later on in the build. Okay, this last demo is called the Vortex. It combines both palette manipulation and additional effects that I can do by modifying some of the other hardware registers here. And I'm very interested to see if anyone can take a look at this and work out exactly what I'm doing. Hey! I'm seeing a very small amount of corruption at the top of the screen. I need to check my palette update code. Oh, that's absolutely awesome. Okay, with that high note, I think we can say that the palette hardware is absolutely working, and that's a brilliant success. I'm overjoyed with this. Okay, that's awesome. It was actually really fun being able to make a more extensive breadboard circuit, which I haven't been able to do for a while. But the net result of adding this palette hardware to the build is absolutely brilliant. Very, very pleased with how it came out. It's exactly what I was hoping for. So I've only got two major components left in the VGA build. I've got the tile data and the sprite hardware, both of which I know are going to be a nice big step forward in the visual results of the build. There's also a whole bunch of work I need to do just to integrate everything down into PCBs. And I think there's at least one video just discussing the timing and the way all the different modules are going to connect up to one another. As always, big thanks to all of my patrons. I really appreciate your support. And I hope everyone found this interesting. Thanks a lot for watching. I'll see you again soon. I'm going to leave you with a longer view of that final demo, which I'm really happy with, very pleased with how it came out. If requested, I might do a small video on my extras channel telling you exactly how all the components of that work.